Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be continuing our discussion of optical diffraction by looking at diffraction through circular and square apertures. And actually I'm going to kind of go in reverse order from what the title indicates. It just sounded better to call it circular and square than square and circular for some reason. So what do we want to recall for this video? What should you be familiar with before watching this video? Well, you've already hopefully watched the video on interference from the double slit at the very least, and on diffraction through a single slit. So we basically have our double slit and our single slit patterns, and these are both formed due to effects of essentially adding up interference from a bunch of point sources within either the double slit or the single slit, as the case may be, and looking at what the phase differences are. Of specific importance for the intensity is the intensity for a single slit. We had the location of the dark fringes. So you had dark fringes at locations such that basically the slit width A times the sine of the angle was equal to the order times lambda. So m here represents the order. If m is equal to 0, you actually get a bright fringe. That was the kind of weird exception to this. Okay, and then the overall intensity pattern was given by a sinc function. So the intensity pattern for a single slit came from the sinc, specifically I of theta, theta being your angular position relative to that slit on the screen. I of theta is the central maximum intensity times the square of the sinc function of pi times slit width times sine of theta divided by wavelength. And again, that goes with the geometry such that you have a single slit of width A, and you are projecting this onto a screen, somewhere far away, such that this right here defines your angle theta. This is perpendicular. This is your angle theta. And so this would be I of theta at this location. I naught would occur right here in the center. Okay. For the double slit, obviously it was proportional to a cosine squared and the distance between the two slits, but we're less interested in that today. So what happens if you have a square aperture or a square hole that you are shining the light through? For that matter, what happens if it's not a square but just rectangle in general? Well, the assumption for the thin slit was that the slit itself was very, very long compared to its width. So you'd end up with something somewhat like this, where this right here might be the slit width A. And the pattern then, if I had a screen somewhere over here, the pattern is being swept out in this horizontal direction, theta. So basically in the same orientation as the slit itself. So we really ignore any pattern that's vertical or oriented along the same direction as the tall part of the slit. In other words, if I were to draw a vertical and horizontal axis here at the location of the slit and another one here at the location of the screen, the entire pattern and theta and all that are defined entirely in or along or parallel to the horizontal direction rather than the vertical direction. So the reason for this assumption is that this dimension here, whatever the height of the slit is quite large compared to whatever the width of the slit is. So for a square or even just general rectangular aperture, basically what we do is we do away with this assumption that this height is very, very large compared to this width. We basically say, well, what if h is not many times greater than a? And the answer is actually fairly simple. Instead of having a very tall, very long slit, you now maybe have a slit that's more like this, where I have the width and then the height basically oriented this way. And the thing is that now, instead of just being along a horizontal axis, I expect to get a pattern along the vertical axis. And that pattern actually behaves similarly to the pattern along the horizontal axis, such that if it is a square wave, the two patterns will basically look identical. And so you end up, because they are not equal, you end up with two slightly different patterns. Basically, you just go back to this equation, and maybe now instead of a theta, maybe you have a theta and a phi. And so instead of I of theta, you might have I of theta comma phi, where if I were to draw my two axes again, like so, I basically could define an angle phi to be essentially along this vertical axis, whereas my angle theta would be along the horizontal axis only. Okay, and basically I expect for this equation to work out basically the same as before, where I have the sinc squared function just as before, pi a sine theta over lambda for the horizontal part, so pi a sine theta over lambda, except for that now I have a vertical component as well. And so this ends up looking like pi h times sine of phi over lambda. And so essentially what I end up getting is a pattern that looks more or less like kind of a cross shape, to be honest, because everything tends to fade as you go away from either of these axes. And so my overall pattern when I have just a square aperture or even a rectangular aperture tends to be cross-like. And so what that may look like is this. You end up with kind of this cross pattern. In this case, because the height is relatively long compared to the width, you actually end up with a cross that's short compared to sort of like the arms of the pattern. And of course, you would also expect there to be additional sort of like spots filled in to here, and they get kind of dimmer as you go away. That's kind of hard for me to draw very practically, so I'm just going to kind of put some little dashes in here to represent that that's going on, and then I'll just paste in a picture that somebody took very nicely and posted onto Wikipedia. I do have some pictures of this that I've done myself, but I don't have any very good ones at hand for this video. So here's the sort of like version of somebody else's. I took a picture and loaded it up, and you can see kind of the cross pattern. You can even tell from looking at this that similar to what I've drawn here, we may have a different height than width present, although mine's a little bit more exaggerated. All right, so that's what happens if you have a rectangular or square aperture to pass through. What happens if instead your aperture is circular? So what if we have a circular aperture? Well, in this case, you have total symmetry about your sort of aperture. Okay, so instead of having sort of a length and a width, you may have just kind of a radius somewhere. And then you would expect on the screen far away, therefore, to have a more symmetric version of this. And so instead of having individual bright and dark sort of spots in this cross-esque pattern, you actually get bright and dark rings. Okay, so this right here produces a set of bright and dark rings. The bright and dark rings, they're sort of like brightest at the center, and then each ring as you go out gets a little bit dimmer, sort of like what we see in these other patterns where you have the brightest here and then they kind of just get a little dimmer as you go away from the middle. Okay. There's sort of two ways that you could go about specifying these. One is by specifying how big each of these rings is, like specifying a radius. And the other, which is more in line with kind of what we've done here, is specifying an angle, except for that now instead of the angle just being here's angle theta or angle theta and angle phi, we take what's called just usually we use just angle theta again. And so again, we would have sort of like our straight line to center and then arbitrarily draw out to some given point. And this angle right here now becomes our angle theta. Now, I'm not going to try to describe what this intensity actually is because you do it in terms of what are called Bessel functions, and those are kind of beyond the scope of an introductory physics course with or without calculus. I usually cover them, for example, in a math methods course, which is about a 3,000 level course on the campus that I teach on. Sometimes they get covered in an optics course, which is usually 3,000 or 4,000 level. You can go look them up if you'd like on Wikipedia or Wolfram Alpha, or you can play with them in MATLAB or Python, etc. Mathematica. Any of those. They are kind of beyond the scope of this class. What we're mostly interested in here is, in some sense, like where are the dark fringes located? So the shaded in here, these are bright. So these right here represent the bright fringes. So these are bright. And then the areas that I haven't shaded in would represent dark. So this is dark, 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 and dark. And we're basically, like I said, we're interested in where are the dark fringes, because those are sort of like define how big each of these bright fringes are. And it's not as easy of a pattern as what you get from this or from this, where you can just say a sine theta is m lambda, because these are described by Bessel functions of the first kind. With that said, we can find where these dark areas are in terms of the diameter, we'll say d of, or big D of the circular aperture, and this angle theta. So where are the first few of these located? The first four of our dark fringes are located by these angles. Sine of theta 1 is approximately 1.22 times wavelength over diameter. Sine theta 2 is approximately 2.23 wavelength over diameter. Sine theta 3 is approximately 3.24 wavelength over diameter. Sine of theta 4 is approximately 4.24 wavelength over diameter, etc. Notice that for the first four or so, you're basically just incrementing this first number by approximately 1.01, although that pattern does not hold linearly as you get to larger and larger values. Now, with that said, of all these, one is kind of more important than the rest. Specifically, this first dark fringe location, that would be this innermost circle right here. And actually, if we're calling it the dark fringe, that would be basically like to this ring right here. So we're assuming that it gets dimmer, 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 darkest at this green, and then starts getting brighter again, brightest somewhere in the middle here, etc. All right, so that ends up being kind of our most important one for our purposes. That's what's sometimes called the airy disk. And it's named after a astronomer from the Royal Astronomical Society who kind of sort of not so much discovered, but kind of like discovered that this was a thing. And this airy disk, the reason why we care so much about it is because that central bright one is actually much brighter than all the rest of the rings, to the point where it actually sets the resolution limit for a circular aperture. Basically, the airy disk imposes a resolution limit. And that resolution limit is if you have two objects that are both acting as point sources, then each of those two objects is basically creating a sort of airy disk, which is what's actually visible when you look at, say, like a distant star through a telescope. You get the star's airy disk. And this is also true if you're looking through a microscope at something very small. You have two objects, 2 points on, let's say, a cell that you're trying to resolve from each other. Each one of those is sort of like a point source and has its sort of airy disk associated with it. And you can resolve two objects if the dark point of one object's airy disk overlaps the brightest part in the center of the second object. So these 2 point objects, which I'm representing by a couple of black spots, and then I'm showing sort of the airy disk for each of these. These are kind of what we call like just resolved. And if they were a little bit farther apart, then they're more readily resolved. If they're a little bit closer together, then they will tend to be not resolved, but instead may look like a slightly larger or brighter or more extended object. So here we have our just resolved, and it's like you can kind of make out that this is not just one object anymore. Here they're quite well resolved and you can see them both distinctly, and here they're not really resolved. It's not clear that this is two objects rather than one object. Okay, and so this is what is sometimes called the Rayleigh criterion. The resolution limit, sometimes specified as a theta resolution, sometimes as delta theta, whatever you want to use to specify it, is that this must be greater than approximately 1.22 lambda over d. So if the objects are closer together than this, then they won't be properly resolved. You won't be able to tell that you have two objects. Instead, you'll just get one object. If they're right at the resolution limit, maybe you get something that's kind of lobed just enough that you can tell that there are two. And if they're farther apart, then maybe you get two very distinct objects. And this is what's again called Rayleigh's criterion. Historically, it imposed some interesting results. For example, this discovery of a resolution limit and of the airy disk was one of the major things that was used to determine that the so-called fixed stars are actually farther away than what the original calculations would suggest. The fact that they had airy disks to them. Because when we look at a star through a telescope, it has some finite size, and that's due to the airy disk. And so you can scale that finite size to, say, the size of the sun when you look at it through a solar telescope. Don't look at it directly through a regular telescope. You'll blind yourself. But if you look at it through a proper solar telescope, you can get an estimate of the sun size. You can get an estimate of how far away the star is by basically scaling the airy disk size to the sun's size. And of course, this makes the basic assumption that the sun and the object you're looking at are the same size, which is not entirely a true assumption, but maybe if you look at enough of them, then you can say, okay, on average, thereabouts. Or if you look at similar stars to what the sun is, similar color, that kind of thing. Then yeah, you can try to get an estimate. And the problem is that your estimate's wrong because you have an airy disk size imposed by the telescope that you're looking through, and that size ends up being somewhat larger than the actual apparent size of the star, and therefore it makes the stars seem closer than what they actually are. And so this is an important piece of information used to sort of confirm or deny the different models of the universe in which we asked, does the Earth move or does the sun move? Does the Earth move about the sun? Does the sun move about the Earth? And one of the sort of last pieces of information that they did not have, certainly not at the time of the Galileo trials, and not even later as Newton was formulating his law of gravitation, was the correct distance to the so-called fixed stars. So once they discovered the airy disk, they now had an explanation for why the fixed stars remained so fixed with a moving Earth. It's because they are actually much, much farther away than what we would have otherwise estimated. So that's all for today's video. I hope that you've learned something from it. Hope you found it interesting. And as always, thanks for watching.